Threadripper is back, but is Threadripper back for Linux workstations? That's what we aim to take a look at. If you picked up a Threadripper system, you might be rocking a 2000 series or a 3000 series. The 2990WX famously worked better on Linux than Windows. But what about the new Threadripper high-end desktop? These are not pro CPUs. They're meant for high-end desktop. They've got a hefty price tag, but the performance is pretty awesome. Let's take a deeper look and let's see how it works with Linux. So first up, thanks to AMD for sending these over so that I could test drive them with Linux. There's a lot of performance here, but there's a couple things that need to be addressed or things you should be aware of if you're going to use this on the Linux platform. But breathtaking performance is not one of those things. It's basically the fastest thing you can get right now, period. DevOps? Yup. Developer workloads and kernel compiling? Yup. Things that need lots of memory bandwidth? Okay, well, you're probably going to need Threadripper Pro for that one. But still, lots and lots of I/O lanes, not as many as Threadripper Pro, but still a ton, way more than desktop. For our benchmarking, we're using the Phoronix test suite for most of our actual real-world benchmarking. But I also use this as a workstation, using Pop! OS as a base, but with the latest kernel 6.x series, because you really need a lot of those bleeding-edge patches for this platform. Okay, you don't have to have them, it actually does work fine without them, but I kind of want the bleeding edge features because you get just a little bit better performance all the way around. Now the first benchmark I'll call your attention to is the memory benchmark. I'm comparing this to the last gen 32-core Threadripper Pro just to give you an idea. This is a 4 memory channel platform, and we're testing this in the TRX50 motherboard from ASUS, which I've also covered separately in another review on the main Level 1 text channel. So if you're more interested in this board, checking it out. It's pretty cool. It's got optional remote management, IPMI, out-of-band management, whatever you want to call that. It's got 10 gigabit Ethernet and 2.5 gigabit Ethernet, the Quantia chipset. It's got lots of PCIe lanes, lots of M.2. It doesn't have any MCIO by 4 or by 8 connections. I really wish that it did, but overall this is a pretty solid board with a server-ish BIOS. It doesn't have any of the gamer nonsense. There's not even a single RGB header on this motherboard. But the first and most important thing is the memory bandwidth to understand this. I think if you're going to get this workstation, you're only going to get it in a 4 memory channel configuration. You can run this in a dual channel configuration, meaning that you only populate 2 of the DIMMs, but it's 1 DIMM per channel. 4 DIMMs, 4 memory channels. It's also registered error correcting memory. This is something that is important to a lot of you, but some of you may not know the difference between error correcting DIMMs and registered error correcting DIMMs. There is such a thing as unregistered error correcting DIMMs. I think this is sort of the final nail in the coffin of unregistered error correcting DIMMs though, because there's nothing not to love about AMD's implementation of registered ECC memory. I could actually go into a whole separate video about how awesome the registered ECC memory is, because even though this is DDR5 5200 as the maximum supported speed, they still managed to get the NPS4, that's 4 NUMA nodes, latency down under 70 nanoseconds with registered ECC memory. This is no small feat. And with a little bit of tuning, you could do like 65 nanoseconds, 63 nanoseconds. It depends on your kit of memory and some other stuff that's coming. But DDR5 6400 is also possible on this platform, those higher clocked DDR5 memory speeds. And you can get into a situation where you've got some impressively low latencies. If you want to stick to JEDEC standards, of course, you can run just no bling server memory. I was using G.Skill's DDR5 Neo kit, so if you want to pick up the same kit, there's a forum thread. You can basically paint by numbers with this machine and be reasonably assured that basically everything works on Linux out of the box, including audio. Everything except S3 Sleep, which is a little rough around the edges. It does work, but it doesn't work perfectly. We'll talk more about that in a minute. And that's going to get fixed with a BIOS update, don't worry. But overall, pretty solid platform. But you still only have 4 memory channels to work with. So you would expect it to be half the performance of DDR4 Threadripper Pro, roughly the same clocks, because it's the same bit width. But no, actually the memory controller is more efficient here. There's not really a huge difference in terms of the raw MBW bandwidth between our 8-channel Threadripper Pro platform running at 3600, which is, you know, beyond what you would get with the registered error correcting memory variant on last gen Threadripper Pro versus DDR5 6400 on the Threadripper high-end desktop platform, the Threadripper 7000 platform, in other words. And it turns out that for developer DevOps type workloads, you really you're not really super constrained by memory bandwidth, but we are testing the 64-core and the 32-core Threadripper 7000 series parts. 32-core I think is going to be a sweeter spot for your Linux workstation, unless you're doing rendering, lots of background tasks, stuff like that. 64-core might make sense for you, but certain workloads do actually have a lot of DDR5 memory pressure. So maybe 48 cores is possibly the sweet spot for these DevOps type workloads, but 32 cores with the higher clock speeds versus 64 cores at lower clock speeds, it just depends on what your jobs are. You're going to have to understand the geometry of your workload to really make a decision here, but I digress. If we look at benchmarks like Rodinia, it's like, okay, yeah, we moved from a 32 core to a 64 core platform, even from DDR4 to DDR5. It doesn't make a huge difference for these computational fluid dynamics type problems. Partly this is an optimization problem, and partly this is because Threadripper Pro 5000 series was pretty darn good in its own right, but we are moving up to PCIe Gen 5 and DDR5. For most of our multimedia benchmarks, it's pretty much the same story. There are some significant core-on-core gains here, but unless you're running lots of multimedia stuff in the background, the difference between 32 and 64 core is really not a doubling. I gotta get my hands on Threadripper Pro to figure out if this is memory bandwidth related or just gen on gen, or just that the optimizations really nailed it for the Threadripper Pro 5000 series. Timed Linux compilation, on the other hand, shows a very significant speed up, and that's not something that historically scales well with a ton of cores. So 32 and 64 cores on Threadripper 7000 series versus our 32 core Threadripper 5000 series, Threadripper Pro 5000 series, 8 memory channels versus 4 with 64 cores. It's not exactly an apples to apples comparison, but over 100 second savings in the all mod config kernel build, pretty darn good. Gromax on the other hand, more cores is more better, right? More cores, more Zen 4 cores is more better. Nearly a doubling from our older Gen 32 core part to our newest generation 64 core part. Not bad. OpenVINO is one of those really interesting benchmarks. OpenVINO benefits tremendously from 7000 series Zen 4 cores. Also experimented a little bit with ZenDNN. I don't really 100% know what I'm doing here, but running ZenDNN, limiting myself to 32 threads on the 64 core platform versus the 32 core Threadripper Pro, it seems that this workload does benefit from the extra memory bandwidth of the Threadripper Pro platform because the performance parity is pretty similar. Meanwhile, increasing the batch size to 64, yeah, we did double the performance. So is it that there's more residency on each individual core, like everything can live in cache? That would seem to suggest that it's not a memory bandwidth issue, but then on the other hand, I don't know. I'm not sure what to make of that result. I'm also not 100% sure what to make of our OpenCV results for image processing. For video, it's about like I'd expect. Zen 4 is just raffle stomping everything. But for image processing and everything else, it seems as though it's more I/O bound or more bound for the rest of the parameters of the system. It doesn't really matter as much in terms of like per core performance. Now in terms of gaming, you might have noticed that I've got the ASRock Aqua 7900 XTX in this system. And boy howdy, let me tell you, this system can game. If you're a game developer and you're developing on Linux and you want to run Windows VMs, I'm still working on the IOMMU testing. That's not quite done, but Proton is what I'm talking about here. Everything Steam related, everything native to Linux, it is breathtaking gaming performance. It is really amazing. And again, 64 core versus 32 cores. 32 cores is really the sweet spot for those kinds of performance, but hey, you want to play Baldur's Gate at a bazillion FPS on the 7900 XTX natively via Proton under Linux? You can do it. Perhaps one of the most remarkable things about this is that Pop! OS with admittedly some tweaks and updates for Mesa and video drivers for the 7900 XTX, the latest kernel, etc., etc. We're basically at performance parity with Windows. It's really close, shockingly close. Will 2024 be the year of the Linux desktop? It can't get here soon enough. Probably not. But I love that Linux works as well as it does for desktop and productivity tasks at this point. It's not just server that Linux has completely taken over the universe. Oh, we're trying on desktop. Woo! Let's talk computational fluid dynamics. I don't have access to a lot of software to do this. I've asked ANSYS and many others for access to software in order to do this kind of testing because this is right up our alley. Physical simulation, like if you're an inventor and you need to test like how radio waves are going to interact with things, or PC board losses, or fluid dynamics that we always talk about. It's nice to be able to simulate those things, and that's basically becoming a commodity, which really helps lower the number of prototypes that you need to do anything. This is used extensively in microprocessor design, even just like a newer, more efficient washing machine. It's really awesome. Thanks to the awesome people in the Level 1 Techs forum, I've been able to get access to COMSOL and run simulations with COMSOL. So running this particular simulation with COMSOL in our 128 gig Threadripper high-end desktop machine, it's about an hour and 9 minutes. And to put that result in perspective, with a 64 core machine, okay, that's pretty cool, but our Xeon comparison system takes over 3 hours to run. That's not exactly an apples to apples comparison because I don't have a large library of these systems yet. I only just got access to COMSOL because, again, awesome level 1 text forum community members, but this is really cool. One reason that you might want to go with Threadripper Pro, though, is that instead of 4 memory channels, you have 8. This is a program that not only uses compute, but also memory. It's a lot easier to build a system that has 512 gigabytes or a terabyte of memory when you have 8 memory channels instead of 4, because you can just use physically more DIMMs. That's also faster. Another reason that you might want to do that is the people that make COMSOL and ANSYS and other software like this generally tend to certify the Threadripper Pro platform first. AMD has been so relentlessly and so consistently executing on their high-end and workstation platforms that now software companies are taking notice and they're going through the motions to say, yes, an AMD platform will work fine with our software. Very exciting to see, and the results speak for themselves. If you are feeling adventurous with this Asus TRX 50 motherboard, you should know that the Gen 4 U.2 connection on the front, I try to use it with just regular old Gen 4 cables. You're probably going to need cables that have a built-in redriver to use it with a Gen 4 SSD. I've also got some Kioxia CM7 drives, those are Gen 5, and those work fabulously well off of PCIe like 8-lane and 4-lane MCIO connectors on server-class motherboards. We really need those 4 and 8-lane MCIO connectors on motherboards to be able to take advantage of all of the PCIe Gen 5 lanes that are available. I mean, yeah, sure, the PCIe slots themselves are Gen 5, but Gen 5 storage, like the Kioxia CM7 Gen 5 SSD in a workstation like this would not be unheard of. And that's really where we should be when we're doing high-end desktop versus consumer-grade Gen 5, in my opinion. But, you know, that's maybe a video for another day. I'm Whittle, this is Level 1. I'm signing out. You can find me in the Level 1 forums. If you have any jobs or anything that you want to run on this platform, let me know. Let's take a closer look.